Good afternoon. Now, I wonder, did you ever stop to think why something so ubiquitous in the modern built environment as rising damp doesn't seem to have been a problem in the past? There's no sign of anything like damp-proof courses that we can find in all the thousands of years of building before the 19th century. So what's going on? Like most of us, I was brought up originally with the damp in buildings coming from four sources. So dispersed water, which is just a fancy name for rain, essentially, condensation, hygroscopicity, fancy word for something like salts attracting water molecules, and of course, rising damp. And I went on to teach those too. But I found myself getting more and more worried because, as you'll know if you've ever seen any of my talks before, I always like to have pictures to illustrate things, but I could never find one of rising damp going much higher than just above the skirting board or the first course of bricks. Every time I thought I'd found it, it turned out to be something else. I had really high expectations when I went to Venice eventually, but even there it didn't come up trumps. My conservation architect friend who lives there confirms that all that damage to the brick is due to wash from boats, and that's something that's become extra obvious since the lockdowns began. At least I was in really good company because, as I found out, even the BRE couldn't find significant rising damp when they wanted to field test damp-proofing treatments and went everywhere looking for a wall with rising damp to test them out on. Every time they found one, it turned out to be some other cause. And eventually they found what they thought was the perfect site on a garden wall at Stowe. I think it was. This wall is certainly at Stowe. I don't know if it was this wall. And they came in with all their testing equipment and they put a tent over everything to keep it safe. And the wall dried out. It turned out to be faulty coping stones letting water in at the top, and that's such a common problem. Gravity carries that water down through the core and it builds up from the bottom. You see this sort of thing all the time with faulty parapet gutters and cracked flashings and flaunchings too, so the water goes down and builds up from the bottom. Anyway, the whole rising damp thing sat there as a nagging puzzle in the background until Brian Ridout and I started writing the PBC Building Environment volume. We compared notes then, and we discovered that neither of us had actually ever seen groundwater rise above those first couple of courses of brick, even in really bad conditions. So we were forced to get our thoughts clear. Brian went off to look through the archives, and I went back to the physics. Now, the thing about water in buildings is for something so ubiquitous, it's actually really poorly understood, or perhaps that's because it's so ubiquitous, because we really don't stop to think about it. And to make things worse, we don't really have the right words for things. If you take permeability, for instance, we know what that means in a lab. In a lab, it involves a saturated tube of material, and it's the speed that the liquid will travel in from one side and out the other when it's driven through that material by a pressure difference on either side. But that's nothing like a wall. Even in a flood, you don't get that sort of saturation or that sort of pressure. So what is it we're really looking at? What is it that we really mean when we say a wall is permeable or breathing? The first thing to remember is that when water hits a building, things happen at different scales. You've got the building scale where you're thinking of things like joints and gutters. You've got the microscopic scale where you're thinking of what's happening right down at that pore level. But you've also got that middle scale where you find lots of other ways that water can travel, like through cracks and voids. And it's that middle scale that doesn't actually get looked at very much. But as far as we can see, it's really important, and perhaps even the dominant scale if you're trying to understand how water really moves in a real building. Now, I don't have the time today to go into the background details of the science of things like capillary flow, but if you want to get the whole picture, you can tune into the two Common Sense Damp webinars that I did back in January and March, and you can link through to those on our Technical Tuesdays page. So let's follow water from the time it's just molecules in the air to the time it forms rain, to that rain hitting the building, and then what happens to it. So water vapor is water molecules in the air, and they are tiny. If a water molecule were the size of a billiard ball, then the billiard ball would be the size of the Earth. In the air, these little tiny molecules just bounce around randomly because they're far too small to be affected by gravity. And the fact that they're smaller than all the other molecules they're displacing in the air means in fact that water vapor doesn't just fall, it rises. Each molecule is going to travel along in a straight line until it hits something like another molecule, which will knock it off course. And that's going to happen more often if you have more molecules. And so the upshot is if you have a lot of molecules in one area, they're going to move towards areas with fewer molecules, which is another way of saying that water is going to move from an area of high pressure to an area of low pressure. And the important thing about water molecules is that they're polar. They have an electrical charge, and that means they stick to other charged molecules, certainly other water molecules, but also things like salt ions, and that's what makes water such a brilliant solvent. So if two water molecules hit each other, there's a pretty good chance they're going to stick together, and that's how clouds form. And eventually you might get enough molecules sticking together to make a drop of liquid that's heavy enough to be affected by gravity. But it's going to startle you to see just how many molecules that takes. In a single raindrop, there is something like 1.4 by 10 to the 21 water molecules. So that's a lot. So that raindrop falls down and it hits a building. Let's imagine it hitting the gherkin. When it hits something smooth and waterproof like that glass surface, it'll bead and then it will run down the surface, collecting any other water droplets that it happens to meet as it goes. And so you can quickly end up with a really substantial flow of water running down the building. And now we need to bring in that bit about capillary action, which comes from the fact that on either side of a curved liquid surface you get different pressures, and the sharper that curve, the greater the difference in pressures. And that's why water rises up in straws, and the thinner the straw, the higher it rises. But you get exactly the same thing happening if you have two flat surfaces pressed together or a fine crack or something like that. They're all capillaries, and if liquid water hits them, it can be sucked in. Once you've got a capillary that's full of water that's connecting two sides of something, then the water can be drawn through from one side to the other like a siphon by the pressure difference. And you can see it here, I hope, in the circled area, that little jet of water that's coming out from between two flat metal plates on this prototype flood door. It took a while for that jet of water to get started, but once it did, it kept going for just as long as there was a water supply on the other side of the door to feed it. And that's why we get so many problems whenever we have water pooling. So on a flat roof or a parapet gutter or a hollow in a wall, if there's a hole to be found, that puddle's going to find it, and then all the water in the puddle is going to be sucked in. So a very tiny little hole can cause a very big problem. Plants evolved amazing cells to exploit capillarity, and they're exactly like superfine straws to get water and nutrients up to the branches. And if you add in evaporation, pulling water out from the leaves, you can draw the water up tens, even hundreds of meters, which is really amazing stuff. And of course, that's where the theory behind rising damp comes from. But the pores inside a porous building material are absolutely nothing at all like straws. They're complex and they're roughed, and they connect to each other all over the place and connect to the surface all over the place too. So you have a lot of sideways movement and evaporation, and the more surface evaporation you have, the lower the rise of water in the wall. And since the beginning of the 20th century, and especially since the Second World War, we've been really veering away from our long tradition of building with porous building materials. We use more and more waterproof things like cement and glass and metal and plastic, and now we even try to make whole building envelopes out of these materials. The old head of the Building Research Station called these raincoat envelopes. But there are a few problems with the raincoat way of doing things. I've already mentioned pooling, but a worse problem is that you can never get raincoats, of course, without joints somewhere. And those joints make perfect capillaries. And when you combine that with a flow of water running down the surface, you've got to be really careful how you detail those joints to stop wicking the water through. It's not helped by the fact that pretty much all raincoat materials also expand and contract a lot as the temperature changes, and your joints have to stay waterproof through all that movement. And hence things like those incredible batten rolls they have on lead roofs, metal roofs being one of the few traditional raincoat elements in buildings. Now, glass must have caused all sorts of trouble when they first started using it to close off windows. Everyone talks about how those big stained glass windows led to flying buttresses as a characteristic of Gothic architecture. But for me, the really big impact that the glass had was on the invented window detailing, things like sills and hood mouldings, label stops, drips, all of which they will have had to come up with to stop the walls getting wet from all the runoff from the glass, which was an entirely new problem. Detailing something that Roger's going to talk more about later. The other problem with raincoats is they stop the water getting out as well. So if you have penetration or a gutter leak or a plumbing leak or condensation on the inside, anything that's putting water on that wrong side of the envelope, if you like, it's really hard to get rid of it. You have to put drains to the exterior and hope for the best. But raincoats is not the way they built in the past. The traditional way of keeping water out was to use what the same head of the BRS called greatcoats, so thick walls made of porous and permeable materials, just like a greatcoat. Now, in simplistic theory, water could get into all those pores and then right through the material. But in practice, it doesn't. And that's because most of those pores are full of air. So if we zoom in to water hitting something like a dry brick or stone or earth wall or lime mortar, what happens is that the raindrops just held in the pores that it hits on the surface. It doesn't run down, but it can't get in any further either because of the pressure of the air that it's trapping in the pores behind those surface pores. It just sits there till it evaporates again. And the only time a raindrop's going to get in any further is if it just happens to hit a pore that's the mouth of a capillary that's already full of water, and then that water will draw the raindrop in. But as long as the wall's in halfway decent condition, that's almost never going to happen because rain's not like a hose. Even in the worst storm, the likelihood of 2 raindrops hitting the same pores is tiny. And anyway, we see this even with flood water. We're currently doing some flood experiments with Liz Laycock at Sheffield Hallam, and when they tested their system on a modern cavity wall with engineering brick and cement, which is a raincoat system, it didn't resist the flooding at all. The water just went straight through as if the wall wasn't there. And we think every joint between the brick and mortar acted as a siphon. But this 9-inch wall of handmade brick and lime mortar in the picture here is still happily holding back the full head of water after more than 8 hours. Now, they often say permeable walls are like sponges, and that's absolutely true, just as long as you remember that a sponge won't take up water when it's dry. You do have to get it a little bit wet first. You have to have some liquid-filled capillaries open to the surface to grab that water. All real walls are going to have some of those, of course, and it's fine as long as there aren't too many. And in fact, it's actually a good thing to have a few because that means that the water can also grab onto the water vapor in the air, and that's how it can buffer changing humidity in a room, for instance. Now, I'd love to go into why you don't get water vapor traveling through a wall at all, despite what you may have heard, but I don't have time today. You can catch up on that in those Common Sense Damp webinars. But what you basically need to know is that if water is traveling through a permeable material, it is going to be traveling as a liquid through the connected up pores and cracks. And where it travels and the speed it goes is driven by things like the way it clings to the surfaces, by gravity, of course, and local pressure differences. But the biggest driver of movement in a capillary or a crack or something like that that opens out onto the wall surface is the water evaporating out into the air. If you try to move the liquid through the pores too quickly, if you try to speed it up and perhaps to dry it, you'll break that flow and then the movement will stop. And that's because the water in the break will be vapor, not liquid. It isn't going to care about gravity, and it's not going to be drawn along by the liquid. All it's going to be reacting to are the walls of the pore around it as it bounces around. And that's why if you try to dry a wet wall too quickly, it's really counterproductive. The drying stops, the bulk of the wall stays wet until all those liquid flow paths have a chance to be able to develop again. The other thing that happens when the liquid water evaporates, turns to vapor, is that any salts or other contaminants that the water is carrying, and water in a wall is always carrying contaminants, salts, clays, all sorts of things, the vapor can't carry them, so they're all just dumped where the liquid flow breaks. Now we know we get the worst problems. We get repeated wetting and drying, and that's why you get that classic damage pattern at the zone at the top of a wet bit of wall. That's often taken to be a classic sign of rising damp, but you can see the source of the water doesn't actually matter. Once you've got water building up at the base of the wall from whatever source, you have weather changes that change the evaporation rate, and you're going to get this pattern. And indeed, none of the photos here actually shows rising damp. That's the trouble with trying to diagnose from a symptom. The same symptoms can be produced by all sorts of different things. And it's not just about misdiagnosis. If you try to base your remedies on the symptoms rather than getting in there and identifying the real source of that water, you're going to risk not just not solving the problem, but doing things that could actually make it worse. And there's common things like cement renders. We'll not talk about those today. They're too obvious to most of the people on the call, I should think, as being a bad idea. But here's another example I see all the time. Putting in perimeter drains, which of course of itself is certainly not a bad thing, though if I were doing it, I'd prefer they're a little further away from the footings if I could get them further away, so when they leak, they don't leak straight into the wall. But the problem is, in this country, the trenches are then often backfilled with gravel, supposedly to encourage evaporation, but sadly they do exactly the opposite. The water will run down easily through all those massive pores, but they're not capillary, so it won't be able to rise up again. So it's stuck in there at the base of the trench, and it can't get out again. Now that's fine if what you were doing were making a true French drain across the hill to stop runoff, but you really don't want to be doing that around the base of your building. The gravel might look really nice and dry on the top, but if you scrape down a bit, you'll usually find it sopping wet and full of silt and weeds. And basically what you're doing by putting the gravel there is mulching your drain. And all that gravel also makes it really hard to check for leaks or do repairs to your drains. What you really want to cover your perimeter drains is clay-rich soil with nice tiny capillaries in it. So the surface water is going to have real trouble percolating down through it, but water leaks at the bottom, on the other hand, can wick up easily and evaporate. If you plant the clay with grass, you'll also beat splashback, which is a good thing. I think lots of hopeful remedial treatments are just applied in every case, though, so without any real thought of what it is they might be expected to do. These days, because we have an obsession with rising damp, we think you have to have damp-proof courses through walls to stop it. Now, I can imagine there might be some legitimate use for a DPC somewhere sometimes, but in general terms, what is it that we're really expecting these DPCs to do? For instance, a lot of councils actually have DPCs on their list of things to do to make your building more flood resistant. But what really happens if you expose a wall cut through with a DPC to flood water? Well, it's going to act as a perfect capillary to bring that flood water right through the walls, right through your building envelope, and often right through the slab as well. And it's really common to find the water bubbling up in the middle of the building first. And of course, getting it all dry again when that water's trapped in the slab can be a right old challenge. And that's why we're currently looking at using gravel underfloors instead when you want to install something water sensitive like underfloor heating. So this is where the gravel's absolutely perfect. The water at the bottom can't come up, but if your pipe leaks, the leaking water will easily head downwards and out of harm's way. But all that said, we do sometimes see things that really do look like rising damp, where there's no source from above, like here at the Scottish Church in Soho. So what's going on here? Well, Brian did find the smoking gun on his hunt through the archives. He found that the very first mention of rising damp was in a patent from 1857, and it's for a special tile system that was specifically intended to deal with a brand new problem, the new London sewers leaking into people's basements. And that's pretty much what we always find when we're brought in to deal with rising damp. We find it's coming from a leaking sewer, or worse still, a water main, as it was here at the Scottish Church. And that's not only just a continuous supply of water, and a lot of water, it's a continuous supply under really high pressure, and that can drive water a good way up a wall. And if people think it's groundwater, they often add tanking, those cement renders and so, which just drive it up further. Or they put in pumps, so Thames Water pumps it in and you try and pump it out again, which doesn't seem very efficient. Plumbing leaks inside the building are even more common. than that, and even more rarely diagnosed. And that's not a surprise given how much we love to hide pipes away where we can't see them when they start leaking, but where they can do maximum damage before you notice. It really is madness of what we're doing to our poor buildings, and then we attack the wrong end of the problem. What they call escape of water is such a common issue these days that it's now the very first place I look when I'm trying to understand a moisture problem. It's the thing I want to get out of the way first as a possible cause, especially if the people who've called me and explained they've only had their problem, their rising damp problem or whatever, for a year or two, or if I think that water's looking suspiciously clear. We've got a lot better at surveying drains and hidden pipework with tools like cameras and ultrasound, which is a really good thing. But when you do it, you still need to be aware that you might be talking at cross purposes if you bring in a drain surveyor without explaining that any leak is a bad thing. What they tend to be working for are water companies, and they're just thinking about flow rates, and they don't really worry about a leak that's not losing a lot of the flow in water supplier terms. But those leaks matter to us. And I do mean a lot. They, in some cases, they don't consider it a serious leak if it's losing less than 30% of the flow. And also, drain systems are apt to have acquired all sorts of little hidden things like dead ends and oxbows over the years. They're hard to find, but although they might not be handling much in the way of flow, they can still be sitting there as a reservoir to collect water in storms and then leak it into your building. Luckily, a lot of the time, the building's going to tell you where its problems are. To quote the old head of the BRS again, he really was a genius, all you need to be a good surveyor is 3 tools: 2 open eyes and 1 open mind. Patterns of deterioration can really help you, especially if they're either really recent or really old. A lot of periods of repair, perhaps suggesting that people have tried to fix a really endemic problem and in all sorts of ways and not having success. That can be a tricky one, but at least it shows you what hasn't worked. So there's lots to consider, and you often have more than one problem going on as well to complicate things, because once you've got damp, it can make future damp worse. For instance, you can set up patches that act as to pull in moisture as hygroscopically. You can also ratchet up a problem. If we think of rain hitting a wall with a moisture problem already, then it's going to take up more of that rain, and that's going to increase the likelihood of having water-filled capillaries that reach the surface, which means that you can take up more rain and the whole thing just snowballs. Now, some good news. Our damp towers research showed that that's really easily fixed, at least if you're lucky enough to be dealing with a greatcoat building rather. Just protecting your wall with a lime-based render will help it to dry, and even if your wall is full of voids, the render's going to stop any more rain getting in through the surface. That's what we think they did in the past. We're asking ourselves, did they ever repoint when the joints started to fail? They probably just added a render, and of course that's why we have buildings that have things like diapered brickwork, which was obviously originally meant to be seen, but we know was rendered later on. But the people in the past who were constructing and looking after buildings were part of a system that made it easy for them to try things out, to learn from their mistakes, and to pass that learning on through things like apprenticeships. And they got really good at understanding what works, even though they didn't write it down for our benefit, alas. So we still have so much to learn from the past, great ideas that really work that we've forgotten. And all I can say is respect. And I think that's a perfect note on which to hand over to Roger.